Alright, so we've worked with tangents, and tangents, you'll recall, are a line that will intersect the circle exactly once. The new term here is a secant, and a secant is a line that when extended in both directions will hit the circle exactly twice. So the way to think about a secant is it's an extended chord. A chord is a segment with endpoints that intersects the circle in two different places, and a secant just extends that chord outside of the circle. So you can see in this diagram here, AB is a secant because it's intersecting the circle twice, whereas CB is a tangent because it intersects it only once. Alright, so various theorems will relate the angles that secants and tangents make according to the arcs that they intercept. So let's try to identify some things about this diagram here. In exercise 1, given the diagram with secants AB and AC, scroll down just a little bit, okay? We want to, and tangent DE, we want to answer the following questions. So first off, what two arcs are intercepted by AB and AC when they form angle A? Alright, so angle A out here, if I follow AB and AC, it looks like there's an arc here, and then there's another arc down here. I'm looking for the arcs that are between those two secants. And so one of them was FG, and the other one was KB. Okay. What arc is intercepted by secant AC and tangent DE when they form angle AKD? Alright, AKD is in here. So secant AC and tangent AD are going to intercept this, looks like this arc right here, arc FK. Let me highlight that in a different color. And so, get that written down, arc FK. What arc do these two segments, these same segments, intercept when they form AKE? Well, that's the other angle on that linear pair. And so that arc is described as from F all the way around through G, through H, and back to K. All right, so that's going to be a major arc, and that needs to be written with 3 letters. So this could be arc FGK, or it could be arc FHK. Either way is okay for saying that arc. All right, let's keep on going here. All theorems involving angles and arcs will be presented in this lesson without proof. Now the proofs can be done. We'll come up with those later. We're just going to skip over them and work with the concepts for today. So the angles made by a chord and a tangent, the measure of the angle formed by the chord and tangent will be equal to 1/2 the measure of the intercepted arc. That works just like an inscribed angle. So it's no different. It's an inscribed angle that has one line outside the circle instead of both inside, but it works exactly the same as an inscribed angle. So in circle O, AEB is 252. That's this whole arc out here, right? And so chord AB and tangent CD are drawn. Determine arc AB. So I want to know this arc right in here. Well, first off, that part's easy. So arc AB is just going to be the rest of the circle, right? So it's 360 minus 252, which is 108. All right. To determine angle BAC, which is this angle in here, it's acting like an inscribed angle. It's not technically an inscribed angle, but it works the same way. So angle BAC is going to be 1/2 of the arc that it subtends, which is 1/2 of 108, and that's going to come out to 54. All right, so you have experience with those angles equaling half of their arcs. It's no different here. All the other theorems involving secants and tangents can be summarized in a single statement. So we'll get to that theorem shortly, but what you see here is 3 different diagrams. One diagram has 2 secants with an exterior angle. One diagram has a secant and a tangent with an exterior angle. And one diagram has 2 tangents with an exterior angle. What I want you to notice about this is regardless of the setup, every single one of these, the angle subtends 2 arcs. I'm just highlighting those arcs here. You should highlight them as well if you have a highlighter. There are 2 arcs subtended in every one of these circles. I'm just going to switch colors on this one because this one uses up the whole circle. When it's 2 tangents, it uses up the whole circle. But no matter what, we have 2 arcs in each one. And what's happening here is that the exterior angle is always half of the difference between those arcs. No matter what, if you have an exterior angle, that angle will be equal to half the difference between those 2 arcs. So you have a bigger arc, you have a smaller arc, you subtract them, take half of that. Every time. Okay, so in this example, 2 secants intersect outside of a circle to form an angle that measures 38. So that means that one of these angle P's, for example, would be 38. The smaller of the 2 arcs measures 65. What's the measure of the larger arc? I'm just going to quick draw this circle. I think it might be easier to talk about if I've got a picture of it. Okay, so 2 secants intersect, so let's draw one secant here. We'll draw another secant here. They intersect to form a 38-degree angle. Obviously, I haven't measured that, so we're just going to assume that that's 38. So I've got one subtended arc here, I've got another one here. I know that the smaller one's 65, so instead of using a y, let's put a 65 in there. This one I don't know. I want to know what that measure is. So what I'm supposed to do is remember that that exterior angle, that 38, is equal to half the difference. So if I subtract x minus 65, that's what I'm trying to solve. So times 2 gives me 76. And then just add the 165 over, and x comes out to 141. All right? So it works kind of like those chords intersecting inside the circle where we added the 2 arcs and averaged them. Here we're subtracting the 2 arcs and taking half of that. So half the difference is what we're looking at, half the difference. All right, exercise 4. Okay, so we've got tangent AD. We've got secant AB. This behaves the same way as the double secant because I've got 2 arcs subtended. I've got one here and I've got one here. So I'm still going to do half the difference. And so ED is 42. And find the measure of angle A. So let's put in x in that spot. Okay? So what I know is that that x is equal to 1/2 the difference between the 2 arcs. Now what I need to do is figure out what this larger arc is. But that's easy because it's a diameter. I can tell because it runs through the center. Circle C means C is the center. So this whole thing is a semicircle, and that tells me that the rest of this arc would be 138. And so what I'm doing in my equation is half of 138 minus 42 because it's half the difference. So the difference here comes out to 96, and so half that is going to give me 48. All right, so once again, half the difference, no matter what, half the difference. And that's what's happening here too. I've got 2 arcs. This is the double tangent version. 2 arcs, one little one here at AB, one major one here at ACB. But nonetheless, 2 arcs that I will have to subtract to get angle E. All right, now it doesn't give me the arcs this time in degrees. It tells me that the ratio is 5:1. So I've got a 5x and a 1x. That adds up to 6x. We know that the total circle is 360. So x equals 60, which means that the minor arc AB must have been a 60-degree arc. The major arc must have been a 300-degree arc. And since the exterior angle is found by taking half the difference, measure of angle E would be 1/2 the difference between 300 and 60. That's 240. Half of that is 120. All right, so if you could just remember, exterior angles half the distance, half the difference, interior angles half the sum, you'll be good. And one way to remember that is those exterior angles are usually smaller because they're converging, 2 lines converging on a further away point, whereas the ones that intersect on the inside have a wider angle because they're converging on a closer point. So that's one way to remember that it's going to be bigger on the inside. You're adding the angles on the inside, rather adding the arcs on the inside, and you're subtracting the arcs when you're coming from the outside.